Good morning, everybody. Let's begin. So homework 7 is the one where I handed out the paper in class last Friday, where you're going to have to digitize the water demand curve for the last problem. That assignment's due on Wednesday. It also has some basic channel geometry problems on it. Then looking a little bit further into the future, you've got the phase 1 of the design project on Monday the 4th. So that's a week from today. Oh, 1 p.m. That's not right. And it may not be the right date either now that I think about it. Yeah, the 4th, that is right. But it's 11 a.m. So I just robbed you of 2 hours, right? Got your hopes up? The demand estimation. Now remember, this is a draft submission, and so it doesn't have to be a perfect estimate of the flow rates. I'm going to be awarding points for correctness of calculations, for quality of assumptions, for validity of the data that you've gone out and found. But I don't expect that you'll have everything perfect. That's why this is a draft submission, is so that I can give you feedback on it and you can make corrections before the final submission. So the 3 things you need to submit are the summary page, the supporting calculations, which have been done neatly and not on lined notebook paper, and then number 3 is a brief write-up that explains your sources, your assumptions, and your methods. So the other announcement is I'm involved with a search for 3 new computer science faculty members, and we're doing interviews today during my office hours. So my normal office hours are from 2 till 4. Today my office hours, I'll be finished with the interviews at 3:30, so I'll have them from 3:30 and then I'll stay here past 5 if anybody needs help. And then I'll be available tomorrow, so if you've got questions related to the homework or related to the design project, reach out and let me know. So any announcement questions before we begin? All right. So this is where we left off last time. In our previous lecture, I introduced the idea that the energy equation is different when we're working in open channel flow than when we were discussing closed conduit flow. In the case of closed conduit flow, the 3 terms that comprised energy were the pressure head term, the elevation term, and the velocity term. But when it comes to open channel flow, you can see that the pressure head is replaced with the depth of the water. We still do have an elevation above the datum and a velocity head term. But if we're at any given point trying to assess how much energy is in the water, we have to take into account the depth of the water, its elevation of the bottom of the channel above the datum, and then the velocity of the flow. So here, this problem is saying, what if we know the total energy at a location is 1.451? So we know E, and we know the velocity is 5.5 meters per second. We know the height of the bed above the datum is 0.782. Just to preserve time for other examples that are maybe more meaningful, let me just show you the calculations for this one. So what we do is we say that the total energy is 1.451, and we can rearrange this to solve for y1. So that's what I've done here, is I've rearranged the energy equation to solve for y1. So we've got the energy at 1 minus the velocity head minus the elevation head. So we're saying the total energy minus the velocity head term minus the elevation term, the leftover amount of energy is how deep the water is at that location. So the depth of the water here would be 0.654. This is just a pure plug and chug type problem where we're rearranging the variables and solving for the depth. We'll come back to this a lot when we are doing the non-uniform flow section because we're going to use this energy approach to find out what happens when we drop obstacles in the channel, like a step that the water has to flow over, or if there are obstructions like a channel contraction, or when the channel gets wider, if water's flowing off of a step, then we can use the energy equation to tell us what's the new depth downstream. And so we will come back to this, but for now, remember, when we're Dealing with steady and uniform flow conditions, it's the momentum equation that we use to solve for the flow depth, not the energy equation. One other stray thing that I needed to address is that in open channel flow, most of the time I'm going to use the inclined length and the horizontal length interchangeably. And the reason for that is that we're going to have very gradual slopes, and when the angle of inclination is less than, say, 10%, then the L times the cosine of theta is about the same as the length itself, like 99.5% of the length for a slope of less than 10%. And oftentimes the slopes that we're going to be working with will be 1% or less. And so it really doesn't pay to differentiate the horizontal length with the inclined length. And so when I say the distance between 2 points, that would be a top view distance, but we'll also assume that that is the actual distance that the water is flowing over, even though there is some delta z. So what I'm saying is let's neglect the difference in length between the inclined section and the horizontal section. One thing, though, that takes a little bit of getting used to is when we were dealing with pipe flow, it was possible that water could be flowing up a hill. If it's enclosed in a pipe, then water can flow uphill. Although the pressure will be decreasing, it could be that the uphill section is just temporary and that all of the other surrounding sections of the pipe are downhill, and so there could be a temporary, like, inverted siphon effect. It could be that there's a pump. But in open channel flow, the water only flows uphill just very, very briefly, and on rare occasions, like maybe a water park could have some sort of a ride where the water's going uphill, and it's doing that because there's a really high velocity that's decreasing gradually. But here, we're just going to get in the habit of expressing slope with a positive sign, and then we'll understand that the water's flowing downhill. So I won't bother putting a negative sign in front of S when that's a given in a problem statement. All of the formulas that we'll use, it's already understood that the water's going downhill. So when S is defined, don't think that that means that it's like a net uphill flow. All right. Yeah. Sure.
Will we be looking at backwater in capacity?
We will.
Okay.
Yeah. And so, you know, water surface slope is a different thing. The channel slope, when we're working with steady uniform flow, we're just always going to have downhill is positive slope. You may remember that when you don't have a diameter, you can replace that with 4 times the hydraulic radius. And so that's kind of a substitution that was introduced a few weeks ago. And you probably remember that we can classify different types of flow. There's laminar versus turbulent, which we use the Reynolds number to characterize. And so here's the Reynolds number in terms of absolute viscosity. Here's the Reynolds number in terms of kinematic viscosity. And so instead of velocity times diameter divided by kinematic viscosity, if we've got open channel flow, the way we could calculate the Reynolds number was we would multiply 4 times the hydraulic radius in place of what would be the diameter normally. But more importantly, I think you've got a homework problem due on Wednesday where you're asked to classify flow regime. And flow regime isn't necessarily referring to laminar versus turbulent, but more important in open channel flow is whether the flow is subcritical or supercritical. And we won't get into it very much yet, but we will spend a lot of time on supercritical versus subcritical a little bit later. But what you need to know for the homework assignment is that it's classified based on something called the Froud number. So FR stands for Froud. And here is the expression of the Froud number formula that you can use on the assignment that's due Wednesday. There's a lot of different ways to calculate the Froud number. This is just one. We'll learn all of them eventually. But when the Froud number is greater than 1, then the flow regime is supercritical. If the Froud number is less than 1, then the flow regime is subcritical. So this will be important when we're talking about things like hydraulic jumps, flow under gates, how the water behaves when there are non-uniform flow characteristics. The Froud number is important. Here, the hydraulic depth, Y sub h, is the cross-sectional area divided by the top width. And so if you've got a rectangular channel, the top width and the bottom width are the same. That's no big deal. But if you have a trapezoidal channel, just keep in mind that the bottom width and the top width are different in the case of a trapezoidal channel. And you've got that table 10.1 that has some of the geometric parameters that will help you to calculate all of those elements. In fact, we've got an example here just in a minute where we're going to deal with the trapezoidal channel geometry. So this is how you classify the flow regime, Froud number, supercritical versus subcritical. All right, so speaking of that, let's look at this trapezoidal channel, which we can see from the given data. It's 35 meters across the top. So capital B is 35 meters, and lowercase b is 15 meters. Okay, so what that tells us then is it appears to be a prismatic channel that has like the same side slope on the left and on the right. See how it says t equals 2? What that means is that for each 1 unit of vertical on the side slope, there's 2 units of horizontal on the side slope. So then that means, let me just erase this so that I can say, all right, so B, capital B is 35 meters. That's this distance. But what about the distance here on the sides? Anybody got an idea of what this length is going to be on either side? Did I hear somebody say?
10 apiece.
10. 10 apiece, you're right. So it's 10, 15, and 10. That gives us the 35. Okay? So the first thing this is asking in this example is, given the dimensions of the channel, what's the depth of flow? And the reason why I think it's valuable for us to know this 10 length across the top, so the 10 that we're referring to is this distance. So from where the channel bottom is flat, if we go up, then this length is 10. Same on the right side as well. So why that's significant is that if we know this is 10, and obviously this hasn't been drawn to scale, we want to know what is y, the depth. That's the first part of the problem. What is the depth? So we're given that the t is 2. And so that is how we can know what the depth of flow is that if we have 10 units of horizontal, then that means we're going to have 5 units of vertical, because it is y is 10 divided by 2, 5 meters. So just to draw it maybe a little bit more clearly, we've got 10 here, y equals 5, because the side slopes here, it's 2 to 1. So for every 2 units of horizontal, 1 unit of vertical, so here's horizontal, 10, vertical should be 5. All right, so that gives us the depth, y. So let me pause for a second, and you can calculate the area, wetted perimeter, hydraulic radius, and hydraulic depth. So I'll pause. Feel free to collaborate, check answers, discuss, and all of that. And let's see if we can find out the area, wetted perimeter, hydraulic radius, and hydraulic depth. And hopefully you can see that in the back, because that is a little bit small. Okay, so on the board we found that the depth is 5. So then the area, if the bottom width is 15, the side slope is 2, and the depth is 5. Then the area, according to that formula that's given, is 125 square meters. This formula doesn't make a lot of intuitive sense to me. I know it's correct, but I mean it's not as intuitive as adding together the elements. And so I sometimes like to break the trapezoid down into a rectangle and then 2 triangles on either side, which when combined are another rectangle. And so there's one rectangle that's 15 by 5, another rectangle that's 5 by 10, and by that same approach it's also 125 square meters. So that is the area. Wetted perimeter, we have to calculate this intermediate coefficient that here it's just referred to as W. It's related to the side slope. And so what you should have done is first of all calculated that W is 2.2361. So you'll get errors if you round that off prematurely. If you said that W is 2.2, then that's going to introduce imprecision into your solution. So don't do that. Carry through all of the precision to the very end and then round off as needed. So the wetted perimeter here should be 37.36 meters. Hydraulic radius is the area divided by the wetted perimeter, so 3.34 meters. Any questions on it so far? And hydraulic depth, 3.57 meters. You can think of hydraulic depth as what would the depth be if it was a rectangular channel. Now this one's trapezoidal, so its depth was 5. But if you re-expressed the flow area as a rectangular channel, then this hydraulic depth tells you what is the equivalent depth that gives you the same cross-sectional area. So it seems pretty simple. It gets a little bit more tricky when you're solving for an unknown flow depth in Manning's equation. We'll show you an example of that today. There are solvers out there. You'll get good, I think, at solving equations on your calculator. So last time we looked at a cross-section of water that was experiencing non-uniform flow. Remember, non-uniform flow is when the velocity is changing in the direction of flow. So here, since the depth is decreasing, what that tells us is that V2 would be greater than V1. And that makes intuitive sense to us that, the water is speeding up as it's flowing towards some, I don't know, it's a cliff. Something's causing it to accelerate in the direction of flow, convective acceleration. So this was non-uniform. But in the case of uniform flow, the velocity at 1 and the velocity at 2 are equal. The system is in equilibrium in the direction of flow. So the depth isn't changing. And here, the slope of the channel is equal to the slope of the water surface, and that's equal to the slope of the energy grade line. Sometimes in our book it's referred to as the total energy line. So those 3 slopes are equal. They're all downhill in the case of uniform flow. In the next assignment, one of the homework problems is going to ask you to use this shear stress expression. And the shear stress is based on the slope of the energy grade line. But when you've got steady uniform flow, the slope of the energy grade line is the same as the slope of the channel. So you can just use the slope of the channel on that problem, assuming it's steady uniform flow. Okay, so steady uniform flow means that the water depth is not changing in the direction of the flow, the velocity is not changing in the direction of flow, and the slope of the energy grade line suggests that there's some head loss that occurs. It's not head loss due to pipe friction because this isn't a pipe, but it's friction that the water is experiencing as it flows over this surface. Like this surface is applying a shear stress. It's resisting the movement of the water downhill So the surface is pushing against the water, and in equilibrium, what we know is that the energy that is being lost to resistance is the same as the energy that's being gained as the water flows downhill. So elevation is being exchanged for velocity, but the velocity is constant, and so it's giving up that energy in the form of losses due to shear stress. So here's really the important, this is the main point of the slide, is that delta Z is how much energy is being lost. And if there was no friction, you'd be exchanging velocity for an increase, you'd be exchanging elevation for an increase in velocity. But there's head loss that occurs. And the velocity isn't changing because it's in equilibrium. So between 2 points, any 2 points in the flow field, the delta Z equals H sub F. So the energy loss that we can identify as the water's flowing downhill is the same as the change in elevation. And consequently, all 3 slopes are equal to each other. Okay, so Manning's equation is one way of really easily determining the velocity of flow with some friction factor. And there was a Chezy equation that I think we talked really briefly early in the semester about the Chezy equation and how it was just observed that there was better fit if the hydraulic radius was taken to the 2/3 instead of 1/2, and also end values were derived rather than using the previous Chezy coefficients for friction factors. So a small end value is for a smooth surface, and a high end value is for a rough surface. And so when you're given a range like concrete, 0.011 would have to be like a glassy smooth finish on concrete. You know, the kind that's really slippery when it's wet. You've probably felt concrete before that almost feels like it's as smooth as glass. That would be this 0.011. And you've probably also seen concrete that's really rough, and maybe it's finished with a broom and it has a pretty aggressive texture on it. That would be on the higher end of this range, 0.020. And all these different material types have a range of values, and for man-made materials, it's a little bit easier for us to know what value to use as compared to natural channels. And so it requires a lot of experience and judgment to go out and look at a creek and know what's an appropriate end value that should be assigned when you've got water flowing through a mixture of sediments and rocks and broken rock, rock that's solid, and so on. But whatever the case may be for the end value, what we do is we substitute it into the Manning's equation, and this allows us to predict what the flow of the velocity would be when the conditions are steady and uniform. So just as a first implementation of that, let's say that we have water flowing through a rectangular channel that's 3 meters wide, and the flow of water is 1 meter deep. So the channel would look like this. We've got 3 meters wide, and it's at a depth of 1 meter. And we want to know what would be the flow capacity of that channel. So capacity means cubic meters per second. It's basically saying, what is Q in this case if we've got a slope of 1%, so S naught is 0.01, and it's smooth concrete. So it would be on this low end. So the end value is 0.011. So what you need to do is first solve the velocity, and then second, find the flow rate, because we know Q equals V times A. So Manning's equation will give you the velocity, and then you can get the area because it's just 3 meters by 1 meter is the flow area. Okay, so pop that into Manning's equation and see if you can determine what is the flow velocity for a 1% slope and this smooth concrete. Concrete. Let me show you the calculations here that. It looks like maybe it didn't update. Well, I had a much better looking example that I did today, but I don't know if OneDrive updated this file. So I'll do it on the whiteboard instead. So the 1 divided by 0.011, the hydraulic radius is 0.6 to the 2/3, 0.01 to the 1/2 power. So 6.47 meters per second. Now, if it had been rough concrete, like that broom finish, kind of a rough, aggressive texture, that velocity could be half of what it is. You know, if we had here in the denominator 0.02 instead of 0.011, then that would cut the velocity down to 3 something. So the n value really has a huge impact on the velocity that you're going to find. And then, of course, what we do to find the flow rate, the flow capacity, is multiply the velocity by the area. So 6.47 meters per second multiplied by the area of 3 meters squared means that we're going to have a flow rate of 19.4 cubic meters per second. Okay. Any questions about part A? Okay, part B, I'm going to show how to solve part B on Wolfram alpha because it's an easy way to type in an equation where what we're going to have is an unknown in multiple places in the formula. So part B is saying, what if we want to convey 30 cubic meters per second at a depth of 1 meter, and it's assumed that what we're talking about is the same concrete, where the n value is 0.011. It's still the same slope of 1%. So Q is 30 cubic meters per second, and we want to know how wide does the channel have to be in order to accommodate that. All right, so to do that, I want to introduce that rather than solving for velocity, we'll just directly say Q is the area divided by n, the hydraulic radius to the 2/3, the slope to the 1/2. So Q is y times b divided by n. Hydraulic radius is the area, y times b, divided by the wetted perimeter, which is 2y plus b to the 2/3 power, and then the slope to the 1/2 power. So in our specific example, we've got 30 cubic meters per second, and then the depth of flow is 1, so 1 times b, so that's just b divided by the n value of 0.011. Y is 1, so it's going to be b divided by 2 plus b to the power of 2/3, and then the slope 0.01 to the power of 1/2. So solve for b. You can put that into your Casio. Your Casio will solve that. I think putting equations into those Casios is pretty annoying. I use a different calculator. There's also Wolfram alpha, so let's look at it that way. Okay, so in Wolfram Alpha, we're going to do math input and just type in the equation here. 30 equals b divided by 0.01. See if I can make this a little bit bigger. And then to the right arrow, parentheses, b divided by 2 plus b. Right arrow, parentheses. Now I'm going to use that shift 6, which is the little hat, you know, that gets me into the exponent to the power of 2/3, right arrow, and then parentheses 0.01 to the power of 0.5. So if I type that in right,
Your n is 0.011.
oh, thank you. Good catch. N is 0.011. That's better. Other mistakes. Okay, so now I just click on this, compute, and it's going to graph it. It's going to give me a whole long answer, but then at the end, it'll give me what I'm looking for what is the B, what is the width of the channel, that then gives me a flow capacity of 30 cubic meters per second. So B is 4.26. B is 4.26 meters. That's how wide the channel would need to be to accommodate 30 cubic meters per second. Now the reason why I solved that is to make the point that it's not a linear relationship between width and flow capacity. So 1 meter, this was 3 meters of width. 3 meters of width gave us 19 cubic meters per second of capacity. 4.26 meters gives us 30 cubic meters of capacity. The fact that we have resistance, the resistance isn't only at the bottom of the channel. There's also resistance on the edges, resistance to flow. So if you make the channel wider by 50%, that's not necessarily increasing your capacity by 50%. You have to actually solve Manning's equation, and that's why it's taking the hydraulic radius into account, is that when you take the hydraulic radius into account, which has the wetted perimeter and the flow area, then those nonlinear effects are all accounted for, and the flow capacity is more accurate that way. Okay, any questions about this example? Manning's values, there's just publication after publication of N values that you can use for different types of material. And you can even estimate your own Manning's value if you have like a granular bed, meaning like small pebbles or something. You can estimate your Manning's value by the median grain diameter of the bed material in feet. That's what this equation is suggesting, is you could calculate your own N value. So for example, if you had small gravel that had a mean diameter of 0.5 inches, then what you could do is use Manning's equation to calculate the N value that would apply there. You just convert the 1/2 inch into feet, substitute it into the equation, and then that would suggest the N value is 0.020. But I don't think in this class you'll ever have to guess what the N value should be. That's always given, and estimating the correct N value is just a matter of lots of years of experience. There's specialized trainings, I would suppose, but we won't get into you trying to figure that out. All right, now if we have a trapezoidal channel and we're applying Manning's equation, then that's what this example is getting at. Is, we've got from table 10.1 the expression of the area, wetted perimeter, hydraulic radius, and sometimes it's advantageous for us to write Manning's equation a little bit different from how I've written it so far. So here's Manning's equation, right? I'm going to erase everything on the board except for Manning's equation, and then I'm going to write Manning's equation just a little bit differently. in a way that I think is the best way for a lot of the problems we're going to have this semester. Okay, so this is the same thing as Q equals area to the 5/3, slope to the 1/2 divided by n, and then wetted perimeter to the 2/3. That's the same thing. Because remember, hydraulic radius is area divided by wetted perimeter. So if we had area to the 3/3 power, because that's just area to the 1 power, is the same as area to the 3/3. So area to the 3/3 plus the area that was in the hydraulic radius gives us area to the 5/3. Slope to the 1/2, Manning's n, and then the wetted perimeter part of the hydraulic radius, which is in the denominator, to the 2/3 power. So this is how most of the time I'm going to write Manning's equation in the problems that we've got this semester. And it's, I think, best to write it this way because where y value is an unknown, then it'll just be easier in some of the calculations that we've got to do. But I wanted you to, be aware that you can see Manning's equation depending on what formula book you're working with. Maybe you'll see it written in terms of Q. Maybe you see it written in terms of velocity. It's always just Manning's equation, but you don't get thrown off by seeing it written a little bit differently. All right, so in this problem, we want to find out what is the flow rate if we've got smooth asphalt with the n value given. The bottom width is 3.5 meters. The depth of flow is 1.2 meters. And then here, the side slope they're not directly telling us what is T. And I'm not going to directly tell you either. I want you to interpret the way it's given here and find out what is T. And this is actually pretty easy. Sometimes it's a little bit trickier when they do a vertical to horizontal description. But in any case, what we want to do is find out what's the flow capacity of this channel when the water is going at a depth of 1.2 meters and the slope is 0.1%. And so the way that we express the slope, it's 0.001 is the slope. All right. Okay, so I think what we're looking for here is a flow rate of about 15 cubic meters per second. I calculated the area and the wetted perimeter the old-fashioned way, but if you use the formulas in table 10.1, did you get the same 9.96 wetted perimeter? Yeah, okay. So area to the 5/3, slope to the 1/2, divided by the n value, and then the wetted perimeter to the 2/3. All that together gives us a flow rate of 14.966 cubic meters per second. So Manning's equation is a beautiful thing. It's very useful. It gets a little bit tricky though when you're trying to find an unknown flow depth. If you've got trapezoidal geometry and you're given a flow rate and solving for y, that's when you're going to be a little more irritated at your Casio calculator. So I'll show you ways. We just went over Wolfram alpha. You can use that on your homework. You can't use Wolfram alpha on an exam. So you should be prepared to solve it either with a spreadsheet or better would be knowing how to do it with your calculator, how to solve for y. We'll do several examples in the coming lectures on that. We are out of time for today, so just a reminder that the assignment that I gave you, that handout on Friday, that's due 2 days from now. And then also you should be thinking about the design project. So I'll see you on Wednesday.